Hello everyone. In this lecture I shall discuss the iterative methods such as Gauss-Jacobi's method and Gauss-Seidal iteration method to solve the system of linear equations. We consider a system of n linear equations in n variables, okay, n cross n system. For simplicity I am considering here a 3 cross 3 system. So now this a11 x1 plus a12 x2 plus a13 x3 is equal to b1. I took 3 variables and 3 equations. Okay. Now in matrix form we will able to write it. I just write the coefficients a11, a12, and 3, a21, a22, a23, a31, a32, a33, x1, x2, x3 is my b1, b2, b3, the right hand side, b1, b2, b3. That means I may call it this matrix A. This is the coefficient matrix. This is my unknown vector x. This is my constant vector b. So I write it ax is equal to my b. In matrix form, or in short we will able to write it ax is equal to b. Okay. Now in the previous lectures we have discussed the direct methods. Now when the system is too large, means there are many variables, large number of variables, then the direct methods, even if direct method gives the exact solutions, are very lengthy. Okay, and from computational aspect these are more expensive to create the software, and to compute it is lengthy and expensive, right? So in such circumstances the iterative schemes, the iterative methods, namely the Jacobi method or Gauss-Jacobi method and Gauss-Seidal iteration method, are more convenient and rapid. It is faster than the direct methods, right? Than the direct methods. So for large variables to work with, that means for practical point of view, we use the iterative methods because it is easy to create the computational aspects, right? So more about these iterative methods are well behaved for yield conditioning system, right? Yield conditioning means you think of the sensitivity analysis, means your little change in your the coefficient aij or little change in the right hand side bj, it brings a large change in the solution, right? This system is called yield conditioning system. So to yield conditioning system, these iterative schemes are well behaved, right? So these iterative schemes are preferred over the direct methods. Okay, but since these are all the iterative schemes, right? So iterative schemes needs a convergence criterion, right? We have the convergence criterion for these iterative methods, right? So now before the details discussion of these methods, let me to introduce myself. Professor S.K. Paikray, Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology in Visut, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the convergence condition. However, this condition is sufficient only. Means even if this condition doesn't hold, still it will converge. But once this condition holds, then we get the answer in less number of steps. Okay, the iterative methods to work, the sufficient condition for convergence is that the matrix should be diagonally dominant, right? The matrix should be diagonally dominant. That means either, if you think of row wise, for each row the diagonal element modulus absolute value should greater than equal to the sum of the other elements in that row. Similarly for column, if either one of these two conditions hold, then we call it the methods will converge. Okay, so that means here diagonally dominant matrix can be viewed as follows. If here A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so this is a matrix given. So now from this row wise, okay, for the first row this A11 should greater than equal to the sum of these two, right? I should have my A11 mode should greater than is equal to A12 plus A13 mode, right? This mode plus this mode. For row 1, row 1. In row 2, what will happen? This is my diagonal element. This A22 mode should greater than equal to A21 mode plus A23 mode. And likewise for row 3, for my row 3, here this is my diagonal element. So A33 should dominate the sum of the other two elements, this A31 mode plus A32 mode. So this is the meaning of for each row. Likewise, or we can, in view of this, we can say this for column, for this column, this A11 should greater than the sum of these two, right? I can say A11 mode is greater than equal to my A21 mode plus A31 mode. Likewise, my A22 mode for the second column, this is my second column, A22 mode is greater than the sum of this plus this, greater than A12 mode plus A32 mode, right? And similarly, my A33 mode, my third column, right, third column, it is greater than is equal to here A13 mode plus A23 mode, okay? So if either of these conditions hold, then the convergence is guaranteed, okay? So the meaning of this sufficient condition means if either of these conditions hold, right? If either of these conditions hold, then the answer must converge, right? The answer must converge. And thus method is repeat, and the method is repeat. Now this sufficient means even if these conditions not hold, right? Even if these conditions not hold, however, even if these conditions not hold, right, these conditions not hold, convergence may be achieved. Convergence may be achieved with large number of steps. So what we should do? We should rearrange, right? We should first rearrange it to see that it should be diagonal dominant. So what should we do? Rearrange the system, right? Rearrange the system so as to get a diagonally dominant system. And if it is possible, right? Otherwise, we proceed, right? As far as practicable, we try to make it diagonally dominant. Then the convergence is assured and this number of steps is less, okay? So now let us discuss both the methods. Now since this is a numerical methods and iterative methods, we need some initial values. If not given, right, start with zeros, okay? Start with here x1 0, is here x2 0, is here x3 0, means initial step is 0. We start with this 0. If it is not given, if given, then you start from that, okay? So now to discuss both the methods, we consider a system. Now to discuss both the methods, we consider a 3x3 diagonally dominant system, okay? So now we create the formula for both the methods, right? We create the formula for both the methods here. So let the initial approximation be this. Okay, we start with this initial approximation. If not given. So now we create the formula here, right? Here you should see that this A11, right? A11 should, the modulus of this should greater than equal to this, or column wise, as I have discussed. Now we create the formula. What is x1 here? I create the formula here. My x1 is equal to, bringing all these things to right hand side. Okay, bring this to right hand side. So it is here b1 minus a12 x2 plus a13 x3. Okay, this b1 minus this 2, right? And it is divided by, I can write it minus, and it is divided by this coefficient a11, right? Divided by this coefficient a11. Clear? Similarly for x2, right? For x2 I find x2 is equal to, here x2 is equal to 1 by a22. We create the formula itself here. It is b2 minus here a21 x1 minus a23 x3, and here x3 is equal to 1 by a33, here b3 minus a31 x1 minus a32 x2. So this is the necessary formula. Now the necessary formula for both the methods. Okay, we consider a system, 3x3 system, and it should be diagonally dominated. Okay, aii should greater than is equal to here aij mod for each row, right? Summation of this, as we said. Then the necessary formula, just we create it. Here x1 is this. Now you see the iterative scheme. The initial approximation is this, right? So now at nth plus 1 step, it will be at the nth stage and nth stage, and here for n plus 1th stage it will be for the result of the previous step. Okay, result of the previous step. And for next step here we just take the result of the previous step, right? Previous step. And however it is a dynamic, it is more dynamic in the sense, whatever the improved result is obtained, we substitute here. So at n plus 1th iteration, it is the nth iteration and nth iteration. You see the difference now. So while I want to improve this x2, right, we have a recent value of x1 is at n. x1, this x1 is a more improved value here, right? We write it n plus 1, right? But x3 is still the previous, so it is n, right? So now for n plus 1th iteration of x3, we have a more improved value of x2. So this is a more improved value of x2, and this is a more improved value of x1, right? This more improved value of x1 we substitute here, and this more improved value of x2 also we substitute here. More improved value of x2 is also we substitute here. So means whatever the updated result, this Jacobi method, we just use the results of the previous step. Here n is greater than equal to here is 0, right? Means with the initial approximation we find the subsequent result. For n is equal to 0, it is x1 1, x2 1, x3 1, in that way. One means in Jacobi method we move stepwise. The previous step result is just used in this step, but in Seidal method the previous result and whatever the updated result we get, we immediately substitute it, right? Right? So you see the difference. So here this is x1n, right? X1n, still we have an improved value here. Now this improved value here x1 n plus 1 is substituted here. Now coming to this previous value we are using at the nth step, but from the same steps we are using also. You see the more improved value. This is a more improved value. While we calculate this, the more improved value we have, and this more improved value we have, we just use this more improved value from the same step, right? So the previous step result is used here. Here previous step and the immediate step also used. So in your Jacobi's method, also called Gauss-Jacobi method, the results of the previous steps are used sequentially, right? While we calculate n plus 1, we use the result of the previous step, nth step. We use the result of the nth step. We use the result of the nth step. But while we apply Seidal method, we have our results of the previous step. This is the results of the previous step. Still we improve. Still, while we calculate this, we have a more recent result is here, right? So this more recent result is used here. While we calculate this, we have a recent result. Here x1 is a recent result, and here x2 is a recent result. So these two results are used here. Okay, so this is more dynamic. Seidal method is more dynamic because the result of the previous step and the current improved result also used here. Okay, so let me to solve one example, then your idea will clear. So you are given to solve example 1. A system of equation is like this. The initial condition is given here as 0, right? If something else is given, we'll start by using Gauss-Jacobi's method, or simply called it Jacobi's method, and the second one is Gauss-Seidal method. Okay, so now we create the formula here. Coming to the Jacobi's method. We create the formula here. You see this 20 is superior to this 1 plus 2, and this 20 also here, and you see this diagonal element should dominate. It is dominated. Okay, so now the necessary formula here. Here x n plus 1 is equal to 1 by 20 my 17 minus, bring this to right hand side, minus y minus 2z. It is at the nth step. Okay, and y at the n plus 1 step, it will be again 1 by 20 here. Bring it to this side here. It is minus 18 minus 3x plus z. It is at the nth step. And here zn plus 1 is again here 1 by 20. Here 25 minus, bring this to that side, 2x plus 3y at the result from the previous step. Okay, now step 1. For n is equal to 0, right? Here x at the first step is 1 by 20 is 17 minus y0 minus 2z0, and here y1 is 1 by 20 minus 18 minus 3x0 plus z0, and here z at the first step is 1 by 20, 25 minus 2x from the previous step plus 3y from the previous step. Now as per the given step, previous step, it is 0, so I just substitute it. Okay, so this is my 0, and this is my 0, this is my 0, and this is my 0, this is also 0, and this is also 0 from the previous step. So the result at this step is 17 by 20. It is 17 by 20. 17 by 20 is 0.85, and this result is minus 18 by 20. It is minus 0.9, and it is here 25 by 20 is equal to 1.25. Now come to your step 2. For n is equal to 1. Here x at the second iteration is 1 by 20. It is 17 minus y from the previous step minus z from the previous step. Okay, and here y at the second step is 1 by 20 minus 18 minus 3 from the previous step plus here z from the previous step, and similarly z at the second step iteration is 1 by 20, this 25 minus 2x from the previous step plus 3 times y from the previous step. So I just substitute these results here. Okay, these results here. So what is my x2? So it is 1 by 20, it is 17 minus y1 is 0.85. Sorry, here y1 is minus 0.9. So it becomes here plus 0.9, and it is minus 2 times 1.25. If you simplify it, it is 1.02. It is 1.02, and at this step similarly this will be here minus 0.965, and next will be here 1.1515. If you continue this in your step 3, for n is equal to 3, we have x3 is 1 by 20 times 17 minus y from the previous step, 2 times z from the previous step, and here y next step is 1 by 20, it is minus 18 minus 3 times x from the previous step plus z from the previous step, and my z3 will be here 1 by 20, 25 minus 2 times x from the previous step plus 3 times y from the previous step. Okay, so now the results of this is substituted here to get what is your x3 at the third step. Here x3 will be 1.0009, and this will be your minus 1.0018, and this will be my minus 0.9993. We continue this step, still the results of 2 consecutive steps are nearly same. Now coming to your step 4. In step 4, here n is equal to here 4. We find here similarly x4 and y n is equal to, just one second, it is n is equal to 2 here, it is n is equal to 3 here, it is x4 will be likewise here 1 by 20, 17 minus y from this third step, 2 times z from the third step. Likewise you find your y, likewise you find here z. Okay, you find your z, and if you simplify it, this will give you 1.0000, and it is here minus 1.0002, it is here 0.9996. you see, now these 2 consecutive steps, right, almost approaching. Okay, now we just perform one more step. Okay, step 5, here n is equal to 4, here x5 will be 1 by 20, 17 minus y from the previous step, 2 times z from the previous step. This is plus 2 na. One second, the formula is here, this is plus 2, sorry, this is plus 2, right, this is here plus 2, then this is here plus 2, this is here plus 2, this is here plus 2. Okay, so similarly you find here y5 1 by 20, similarly you find here z5 1 by 20, and this will be calculated to be 1.0000. This is minus 1.0000, this is 1.0000. you see now this is same as this is same as this, and this is almost nearly same as this. Since the result of the 2 consecutive steps coincides, we stop here, we say this is my result. So therefore here x is equal to 1, y is equal to minus 1, z is equal to 1. We may round it up also. So this is my desired answer. This is my desired answer. Now if we perform this by your Seidal method, then the number of steps will be reduced. Maybe in third step we get the result here. Now let us solve this same by using your Seidal method, right? By Gauss Seidal method. So we create the formula now. So now we create the formula. So 20x, solving for x, here x is equal to 17 minus 1 by 20 times here 17 minus this y plus twice z, and this will be computed from the previous step. Right. Now for the second we have 1 by 20, this y is minus 18 minus 3x plus z. Now you see here, for your y we don't have any, for your x we have a improved value here. So for your x we have a improved value here. For z it is still the previous value, it is n, it is the previous value. Now while we find z, it is my 1 by 20, it is plus 3x, it is 25 plus 3x minus 20z. So you see here the x you have a improved value, so the improved value is substituted. For z, this is my 3x minus 2x, it is 3 plus 3x minus, it is minus 2x plus 3y. Okay, so here 20z here, so it is minus 2x plus 3y, it is here minus 2x plus here 3y. Okay, so now you see the improved value of x is there and the improved value of y is there. Okay, the improved value of x is there, so we substitute it, as at the same time the improved value of y is there, right? So this is the difference. But in your Jacobi method, what you are doing, this same is same, but here this is the previous step, and here in Jacobi you have, these are the results of the previous step. So now these values are improved here, this is improved, and this is improved. Okay, so this is why this method is better. Now coming to step 1, for your n is equal to 0, you are getting x is 1 by 20, here 17 minus y from the previous step plus 2z from the previous step. Now here y at the first step is 1 by 20 minus 18 minus 3 times this x from this previous step, in this step itself, x from this step itself, it is 1. Okay, but here z from this previous step, because we don't have the updated result here. Now for your z at the first step is 1 by 20, 25 minus 2x plus 3y. You see here we have a improved result here, so the x is a improved result here, the y is a improved result here, so this improved result will be substituted. Okay, so now first we calculate this. So this is same thing as the result of the previous step, because the value of x0 is equal to y0 is equal to z0 is equal to 0, right? Now this value is my 0 and this value is my 0, so I just substitute it. Okay, it is 1 by 20, 17, so this is equal to here 0.85. So now for this we have, this is my 0, because from this and here this will be my 0.85. I substitute 1 by 20, it is minus 18 minus 3 times 0.85 plus here 0. Okay, if you simplify it, it will be minus 1.0275. So now these two values are improved here. So this is 1 by, so this is my 1 by 20, 25 minus 2 times the improved value of x is 0.85, okay, plus 3 times the improved value of y is, it is minus of 1.0275. If I simplify it, so this will give me 1.0109. okay. So accordingly, coming to your step 2, for n is equal to 1, we get x2, we get y2, we get z2. So this is 1 by 20. Here it is the results of the previous step plus 2 times the result of the previous step. But here the value of x is improved. It is minus 18 minus 3 times here x plus 2 times plus z plus here z plus z, and for this we have 1 by 20, it is 25 minus 2x plus 3y. So now we improve value here. We have a improved value of 1 here, right? This x2 here, and we have a improved value of 2 here and 2 here. But here this is the result of the previous step, because there is no improvement here. Now we substitute this thing, okay. These things are substituted here, and you will get it. It is 1.0025. It is your minus 0.9998. It will be your 0.9998. okay. Now in my step 3, for n is equal to 4, we have x at the n is equal to 2. We have here x3 is 1 by 20. Here the result of the previous step are used here, okay, and this is simplified to get your 1.1000, right? Sorry, 1.00001 means up to 4 decimal places I am writing. It is 0000. So now my y at the third step will be my 1 by 20 minus 18 minus 3x plus z. So this z x is improved from this previous step, but z is from this step itself, and this z is from the previous step, okay. So I substitute it here, okay. I substitute here and z from the previous step. So this will my minus 1.0000. Then coming to my z at this third step is my 1 by 20, 25 minus 2 times x plus 3 times y. So these are the improved result. X is improved third and y is also improved third, okay. If I substitute these values, it will be my 1.0000. You see, now these two steps are almost coincides, or another one step will find exactly the same answer. So here in Seidal method we get the outcome in 5 steps, but here we get the outcomes in 3 steps. So it is twice the faster, okay. So now to conclude, so in general the convergence of Seidal method is twice faster than the Jacobi method. It is in general, not for this particular problem. Now coming to 2 more problems. Example 2, use Jacobi's and Seidal's method to solve this. Now you see here, so here we should have this place should dominant, okay, but you see here it is minus 10. So but here in 4th row we should have this. So just you bring this to this step, and just to interchange these two, right? Just to interchange these two, right? So that this will be my so this should be my first, so that this position will supersede, and the second it should be my second, it should be my 2, it should be my 2, and my 3 it should be my 3, it is my 3, and it is my 4, right? So in that way I consider this, then this, then I consider this, then I consider this, okay. So I just shift it to this place, and I just shift it to the last. Okay, then the diagonally dominated system I will get AI mode is less than equal is greater than equal to my summation of Aij mode over j is not equal to I, right? So then the convergence, so just you rearrange then solve, right? Just you rearrange and then solve. So after if I solve it at my fifth step, the result will be x1, x2, x3, x4. So here x1 is 0.9994, x2 will be 1.9997, and x3 will be 2.9998, and x4 will be minus 0.1 second. So it will be here minus 0.0001. Okay, but in sixth step I am getting x1, x2, x3, x4. x1 will be here 0.9999, and x2 will be 1.9999, and x3 will be 2.9999, and x4 will be minus 0.0001. So therefore what is your solution? Therefore the desired solution here is you see these two are approximately coinciding. So therefore your x1 is just I rounded it to 1, and my x2 is I just rounded it to 2, and my x3 is just rounded it to 3, and here x4 is 0. So this is the answer. Okay, now coming to the last example. Here you see, so this place is larger, this is larger, this is larger, and this is larger. However you see this 10, okay, in row 1 I am getting, in row 1 here 10 is not greater than 8 plus 3 plus 1, or 10 is not greater than here. So here you see the row 1, in row 1 here 10 is not greater than here 8 plus 3 plus 1, 8 plus 3 plus 1, right? But we think this column wise 10 is greater than 2 plus 3 plus 2. Actually the real diagonal dominant is this row dominant. Okay, so this doesn't hold, but this hold. Okay, so here it is delayed convergence, right? It is delayed convergence. Clear? So actually the diagonal dominant here is this condition 1 is here. This is actually the diagonal dominant. Okay, but here or for is this, it is delayed convergence. It is delayed convergence. Okay, even beyond this also we can think of, right? So we should prefer this, right? So here we will get the delayed convergence. Now accordingly if you solve this, we will get the result at the 9th and 10th step. At the ninth step we are getting x1 is equal to 1.0001, and here x is equal to, and here y is equal to 1.0000, and here z is equal to 1.0000, and here t is equal to 1.0000, right? At the 10th step I am getting x is equal to 1.0000, y is equal to 1.0000, z is equal to 1.0000, and t is equal to 1.000, right? So you see here, so the convergence is delayed convergence. So for the exact convergence condition, right, convergence condition should be, this condition is sufficient, right? For each row I here aii mode should greater than is equal to summation of aij mode. So for each row, so j will vary, j is equal to 1 to n and j is not equal to I, right? This should be the condition, right? This should be in if it is not satisfied, we think of the column dominant, right? So however, this is the exact diagonal dominant, right? This is exact diagonally dominant condition, right? This is the exact diagonally dominant condition. So now to conclude, your numerical iterations technique here are helpful for large number of unknowns. Okay, as the student of engineering or higher mathematics, you should deal with many variables. So this, and also it is better to create the computer programming by using the numerical iteration technique. So these are less expensive. Moreover, the Gauss-Seidal method, the convergence rate is twice faster than the Jacobi's method. So this Gauss-Seidal method is preferred over these methods. Okay. So now my appeal to all of you is that if you feel this lecture is useful and interesting for you, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefits. So thank you all. Have a nice day. Thank you all. Have a nice day.